All right, a little skills practice with scientific notation and negative exponents. So in this first one, recall that negative exponents means our standard form is less than 1. So here in number 10, our number is definitely less than 1. So I want my decimal point to be after the 4. So 4.85 times 10 to the 1, 2, 3, 4, 5, negative fifth. Here in number 11, I just move it one place. So 9.3 times 10 to the negative first. And again, it's negative because this number is less than 1. Now, 40,000. There's a couple ways you can think of this. When I see 1,000, I think of times 10 to the third, because thousand, that means it's big. Okay, well, I need 40 is bigger than 10, so I have to move it over 1, and that means my exponent goes up. So we've got like 4, or you could put 4.0 times 10 to the fourth, because it went over and then the 3 became a 4. Okay, in number 13, there are 15 zeros here, or there should be at least. So I want my decimal point to be after the 3. So 3.053 times 10 to the, it's going to be negative because it's a small number. 15 zeros plus that 3 means negative 16. 14, now this is a big number. So 2.4 times 10 to is going to be a positive exponent because 24 billion is bigger than 10. So 3, 6, 9, 10 times 10 to the 10th. In 15, we've got a small number, so I'm going to go ahead and move it after the 9. So 9.83563215 times 10 to the negative third, because I moved it 3 places to get my decimal point after the 9. Now we're going to go the other way, and we're going to go to standard notation. So negative 5 means my decimal goes over 5 places to the left. So the 9 is one place. Everything else becomes zeros. So 4 zeros, 934. Now, in 17, 4 is positive. So I'm going to go 4 places to the right. So the 2 is 1, and then 3 zeros. So 12,000. Just paying attention. Positive exponents get bigger, negative exponents get smaller. So in 18, we're going to go 6 places to the left. So that means 5 zeros, 7881. 9 0, here's the decimal point, 9 to the left, that 3 is the first one, so we're going to have 1, 2, 3, 4, 5, 6, 7, 8 zeros, and then the 3. In number 20, that 1's positive, so we're going to go to the right to make the number bigger. Positive exponents make them bigger. 3 to the left, so 2 zeros, then 5, 4, 5, 3, 9, 9. And now let's do some math. So we're going to multiply 2.31 times, so 2.31 times 2.6, which gives me 6.006 times 10 to the negative 5 plus 2 is negative 3. And there's my scientific notation. Now to go to standard, we take that negative exponent and we move it 3 places to the left. So that 6 is my first place and then 2 zeros. Now let's divide. When I divide, I like to write my numbers on top of each other because that's just how my brain prefers to see them. So when I divide, 9 divided by 1.8 is 1.62 times 10 to the negative 7 minus 2 is negative 9. And there's my scientific notation. Timeout. Totally lied to you. I totally multiplied on my paper, which is how I got that 1.62. When you divide these numbers, you get 5. So 5 times to the negative 9th is scientific notation. Sorry about that. And then when I go to standard, I go 9 places to the left, which means I have 8 zeros before I have that 5. So there you go. Make sure you divide and not multiply like I did in my paper. All right, in 24 we divide. That one's clear, gives us this. So 6.8 divided by 3.2, hopefully I did this one right, is 2.125. Now I have 5 minus negative 2. 2 negatives is a positive, and I have times 10 to the 7th. To go to standard, I move my decimal 7 places to the right. So 1, 2, 3, 4, 5, 6, 7, and there you have standard form. And I believe we have one more. The human body uses red blood cells to deliver oxygen to the organs. An average adult have about 2 times 10 to the 13th 10 red blood cells. That's how many you have. That's total number. Each of those is 2 times 10 to the negative 5th meters long. So this is how many you have, this is how big each one is. So if you put them all together, how many meters would that be? So if we have 2 times 10 to the 13th times 2 times 10 to the negative 5th, how long would that be? So multiply. 2 times 2 is 4. 13 plus negative 5 is 8. So that's scientific. So if I go 8, it's positive. So 1, 2, 3, 4, 5, 6, 7, 8. 400 million meters long if you would line up all of your red blood cells. That is really long. I mean, a meter, think about a meter stick. Think about 400 million of those. That's how long your red blood cells would be if you would put them all next to each other. I find that hard to believe when you think about, I mean, inside your body. How does that happen, right? Like, where are they? But that's where they are. So they're long. That would be long. That doesn't mean they're very wide. So we can pack a lot in there. So that's your practice, I believe. Yep, that's the end.